In this video, we're going to continue our discussion of the Calculus 1 review, and I believe we're on page 6 at this point. And a little bit about this function before we get started is that the function that's given to us here is actually the derivative of some function f. And so while this graph shows us the derivative of f, we can use it to interpret how f itself was behaving. For example, between -3 and -3 and -2, we see that the derivative is positive, right? So the y value of the derivative function is above the x-axis, so the derivative itself is positive. The function value of this derivative is positive. Therefore, the original graph has to be sloping upward. And then precisely at this point here, when x is equal to -2, the original function has a slope of 0, so it's almost as if it reaches this maximum point, a high spot. And then from -2 all the way up to +1, this whole range here, the slope is negative because the y values, or the coordinates of the derivative, are below the x-axis. So we've got this graph that's going to decrease between -2 and +1. Now, what's also kind of interesting is at -1, it looks like our first derivative is equal to 0. Sorry, I meant to say the derivative of the first derivative is equal to 0. And upon further review, our first derivative is the derivative of our first derivative. I got to be careful the way I say that. The derivative of our first derivative is negative through this region, but then the derivative of our first derivative becomes positive after that coordinate. So that tells me that our inflection has changed. So while the function is decreasing from -2 to -1, and it continues to decrease from -1 to +1, the concavity changes right here too. So what was concave down now changes to concave up, even though the function itself is continuing to decrease. The graph then appears to level off again because the derivative is equal to 0 at this position. And a lot of times we think that the graph is going to then turn upward after that, but that's not the case here, because beyond this position, the first derivative is still negative. And so the function continues to decrease. And, you know, this doesn't really indicate the shape of the graph, but it's going to decrease even further. So we're going to drop down further on the y-axis in our original graph. Here again, we have the derivative of the derivative at 4. Sorry, I suppose that's an x value of 3. That's also equal to 0, and we're changing again from a negative derivative of the first derivative to a positive derivative of the first derivative, so our concavity changes again. But the graph is still decreasing after that because the y coordinates of this derivative are still below the x-axis. So we've got lots of decreasing values that are going on, and it's not until finally at this position here where we level off and then our first derivative becomes positive again that we finally see an increasing value in the original function. So even though the question hasn't asked us to perform that sort of analysis just yet, I think it's worthwhile to look through the graph and try to interpret what's exactly going on. Then we can address the questions A through F, it looks like, with a little bit more ease. All right, so at what value of x is f decreasing most rapidly? So we don't know what f looks like, but we would like to know where is it decreasing the most rapidly. Well, the most rapid, the point where it's decreasing most rapidly is where its derivative is most negative, and so at x equals 3, the derivative is the most negative. Or better yet, we could say the derivative is the least. And so along those lines, we're being asked next, which is greater, the function value at -3 or the function value at -2? So again, we don't know what the function looks like just yet, but we're being asked the function value at -3 or the function value at positive 2, well, part of our original analysis indicated that the function is actually increasing from negative 3 to negative 2. So the function value must be greater at negative 2. And again, we're saying that because the function is increasing from an x value of negative 3 to the x value of negative 2. Where does the function f have a local minimum? Where does it reach a low point? Well, here again, our original analysis should help us out with that. Looks like the only time that we're going to reach a low point is here at an x value, and my scale is off a little bit, so 1, 2, 3, 4. At an x value of 4, it looks like we're at a minimum, because that's where our graph changes from a negative derivative to a positive derivative. Now, if we had changed from a positive first derivative to a negative first derivative, then we would have found a local maximum. To answer question C, where is the graph going to be concaved up? Well, concave up means that the second derivative is positive, and that means that the derivative of the first derivative is positive or sloping upward. So the derivative graph is increasing along this domain, and then again along this section of the domain. So if that's where our first derivative is increasing, that's also where our original graph is concave up. That's where our second derivative is positive. And so we would say on the interval from negative 1 to 1, joined with the interval from 3 to, well, we don't really know what's happening beyond this section, so we'll say from 3 to 5. And we're saying that because the first derivative is increasing. Or we could say that the slope of the first derivative is positive. And then where does the graph have inflection points? Well, inflections occur when the second derivative changes from positive to negative or vice versa and equals 0. So we mentioned that in our original analysis. Right here that happens. Sorry, my sketch is a little bit off. But when x is equal to negative 1, that occurs because our first derivative's slope changes from negative to positive, and when that slope changes from negative to positive, our concavity changes from negative to positive. So we're concave down and then concave up. And then again, that happened here. Same thing occurred. But it also happened over here. We changed from a positive concavity to a negative concavity because our slope of the first derivative was positive, and then the slope of the first derivative became negative. So that change in first derivative slopes indicates a change in concavity. So we have inflection points at x equals negative 1, positive 1, and 3. And we know that this is the case because the derivative of the derivative, so essentially the second derivative of x, is equal to 0, and the concavity changed. And our concavity changed. And so remember, we need the second component here. We talked about this weird example in class. If I had, say, x to the 4th power, we'd have a graph that looks a lot like a parabola where it flattens off at the bottom. It's entirely possible for our second derivative to equal 0, and at this point the second derivative would equal 0, but the concavity doesn't change in this case. It's always concave up. So it's not sufficient to say that the second derivative has to equal 0. We have to say that the second derivative equals 0 and our concavity changes. And another way to say that concavity is changing is something like this, the slope of our derivative curve. So the slope of the derivative would have to change from positive to negative or vice versa. And so if we put all of that together, do you think you can create a sketch of this particular graph? Now, it would be important to note at least one initial value. We talked about that in our Unit 5 section of this class. We don't quite know the position of the graph. So if we're going to start by saying that the function value at 1 is equal to 0, that means the graph has to go through this point here, could you sketch the remaining image? And while doing so, I would recommend that you refer back to the analysis that we were performing above. For example, when x is equal to 1, we know that the derivative is equal to 0 and the second derivative is equal to 0. So at this position, we've got the first derivative that equals 0 and the second derivative that equals 0. Over here at x equals 5, and it might be helpful to kind of draw some imaginary lines here. Not that the graph itself is going to be approaching these like asymptotes, but at least it's giving us some reference points to the behavior of this function. But when x is equal to 5, we also know that the first derivative is equal to 0. And then again at -2, the first derivative is equal to 0. And so this gives me some ideas of where the graph is leveling off, where there's a flat spot in the graph. Concavity changes in other locations, and I might use some different colored ink here. Right here at -1, the second derivative was equal to 0, so our concavity changes. And again, at +1, the concavity changed, so I might emphasize that a little bit. And then again at this data point, I think that's 3, the concavity changed as well. And with all of those features kind of outlined, I think we should be able to describe what's happening in that particular graph. On this far left-hand side, we had a positive first derivative, and then on the far right-hand side, we had a positive first derivative. So those are the only two sections where the graph is actually going to be increasing. Everywhere else along this graph, it has to be decreasing. So what I'm thinking to myself is that there's got to be a high spot here. The graph is going to level off right here, and there's got to be a low spot, and I'm going to guess it's somewhere down here. Because again, the first derivatives are 0 at both of those locations, and we're changing from an increasing graph to a decreasing graph. Moreover, the second derivative was negative in this particular region, so I know that the original graph has to be concave down. Over here, the second derivative was positive, so I know the graph has to be concave up. Now, concavity changes at this mark right here, but the function itself has still got a negative first derivative, so the function still has to be decreasing. And so I'm going to try to emphasize that a little bit, if I can. So we're still decreasing, but the function's concavity changes. And then once we reach this position here, concavity changes again. The function appears to level off on account of the first derivative being equal to 0. But then the function continues to decrease after that. And we're now concave down. The function continues to decrease. We're concave down. The concavity then changes to concave up, yet the function still decreases, so we're dropping all along the way. And then finally, we begin to increase. The function's concavity remains concave up in this region, and the function finally starts to increase. Again, on the far left-hand side, we had an increasing function up to this point, yet decreasing the rest of the way through, with several changes in concavity along the way. And so this type of analysis is a bit challenging. It makes you stop and think a lot about the behavior of the function. But for a student that truly understands the calculus that's happening here, I think you'll be able to work through this. It may take some time, but I know you can do it. So moving on from here, I think that's going to be the last question on the no calculator portion on derivatives. We're then going to switch into antiderivatives and indefinite integrals. And so since these are so fresh in our minds, since we just took our test over that, I'm not going to talk through each one. Instead, I'll provide some solutions here for you to compare your work against. And I'll point out that B and D are unlike any of the questions we've seen recently. Excuse me, A and C are very similar to what we saw most recently. And by that I mean we could essentially create power rules out of these two examples if we distribute, in this case, this x, what's wrong with my pen here? This x cubed, if we distribute that into this, we've got a polynomial that we can find the antiderivative of, and for this example we can find the antiderivative of 12 times x to the negative fourth power, and then run with that. On these two examples over here, especially part B, the tendency might be to consider this as a power function, but it doesn't quite work the same way. We've got to be a little bit more careful. 1 over 4 times 1 over x would be appropriate, and we can now consider 1/4 as the coefficient of our antiderivative. That's perfectly fine. That's acceptable. But the antiderivative of 1 over x is not, it does not follow the power rule. We can't simply, I'm having all kinds of troubles with my pen sensitivity here. The antiderivative power rule does not work correctly or the same way when the exponent is -1, because when we increase this to by a power of 1, we get x to the power of 0, which violates some other property. So we got to be careful there. I probably wouldn't even consider that as an option. Well, I might as well just finish this up while we're talking about it. As it turns out, the antiderivative of 1 over x is the natural log of x, because it's the derivative of the natural log of x that equals 1 over x, if you remember that from your derivative rules. So if we're talking about the antiderivative, or the indefinite integral, we need 1/4 times the natural log of x plus c. And we should be careful here because on account of our derivative rules and the domain restriction there, the x value really needs to be greater than 0. And a lot of times we account for that by using the absolute value bars here. So I think that would be most appropriate. As far as part D goes, I would break this into two indefinite integrals. So the antiderivative of sine of x with respect to x minus 2 times the antiderivative of cosine of x with respect to x. And we'll recognize that the antiderivative of sine is the opposite of cosine, and the antiderivative of cosine is sine. I don't need a plus c value twice. I can report it just once at the very end. And I think that would be sufficient. Now with the last two examples, evaluating the definite integrals, I should say these two examples, those again will operate much like the most recent problems that we've seen in class. Some other examples that you may want to be careful of are shown here, C or D. Not that they're extremely challenging, but they both fall in a format that may be a bit unusual for us. So let's talk about part C real quick. I'm going to consider this as the antiderivative from 1 to 27 of x to the 1/3 power. And now I'll use the power rule to find the antiderivative. So I'll raise this to the 4/3 power and divide by 4/3 plus c. And we can evaluate that at the number 1 and 27. Now when I divide by 4/3, that's the same as 3/4 times x to the 4/3 power. Now the 4/3 power would be the same as the cube root of x to the 4th, or similarly, the cube root of x to the 4th power, either one is just fine, plus c, again being evaluated at 27 and the number 1. So again, this type of problem is being asked on the no calculator portion, so you've got to be able to do this one by hand. And this looks pretty intimidating at first, but after you break it down, I think you'll manage just fine. Because 3/4 times the cube root of 27 raised to the 4th power plus c. That one's manageable now if you write it this way. If you had to find 27, or if you chose to find 27 to the fourth power first and then try taking its cube root, you'd have a tough time. But at least here, hopefully you'll recognize the next result. And then in our second component, 3/4 of the cube root of 1 to the fourth power plus c. And so the reason why I said that this is going to be manageable without the calculator, hopefully you recognize that the cube root of 27 is 3. And 3 to the fourth power, while a bit challenging, is manageable. 3 cubed is 27, so you multiply that by 3 again, and you're right back to 81. So now we've got 3/4 of 81 plus c, and I'm ignoring this for a second over here on the right-hand side because that's going to be a little bit easier to do. Now, I don't think 81 has a factor of 4, so it's not like we can reduce this fraction. So I'm going to multiply 3 times 81 and then 4 times 1. So 3 times 8 is 24, or 240, and 1 times 3 is 3. So it looks like we've got 243 over 4 plus c. And now I'll kind of fill in the blanks here. And mental math would be appropriate. The cube root of 1 is 1. 1 to the fourth power is still 1. 1 times 3/4 is 3/4 plus c. And as we subtract those two, 243 minus 3 is 240 over 4. The c values cancel. This c and this c are exactly the same. So when we subtract them, they disappear. And 240 divided by 4 is 60. So a bit of mental stressing or stretching is necessary there, maybe stressing too. But again, it's manageable, I feel. Let's try this last example, part D, and we'll put an end to this particular video. Now, e to the x power, its antiderivative is e to the x power, so that's kind of nice. And we just need to evaluate this at the natural log of 2 and the natural log of 7. And at first glance, you might be a bit nervous about this, but hopefully you'll recognize your power rules. E to the natural log of 7 plus c minus e to the natural log of 2 plus c. Well, anytime you've got the base of e raised to a logarithm with a base of e is just going to be that target, or that argument as a result. So this is actually 7 plus c minus 2 plus c. And the c values will cancel. 7 minus 2 is just 5. Now, if you've got questions on the problems that I skipped, or if you find any disagreements with the answer key that I've got posted, please let me know. I'd be happy to clarify with you as I can. Now, I think that that brings our no calculator portion to a close. In the remaining videos, we'll talk about the calculator permitted portion of this exam. Thanks for watching.